Hi, my name is Muhammad SYAZIMAN bin Muhammad FAIRUZ, and I'm one of the students from class JCDCS 1433C that taking course Science Mathematics in UiTM Segamat. This video is all about one of the subtopic from chapter 2 Logic in Logic and Elementary Proving Method. The subtopic I was talking about is Logical Implication. Before we are going to detail on our subtopic, let's introduce to our few members. This slide introduces all of the members that are going to teach you about logical implications. The leaders are Muhammad SYAZIMAN bin Muhammad FAIRUZ. The rest of the members are Now, without further ado, let's get started on our learning session. Now, you may ask, what is logical implications? The statement, if P then Q, or symbolically P towards Q or arrow Q, is often written as P implies Q. The symbol arrow means implies, so P arrow Q is often read as P implies Q to designate the statement which is the implications of Q by P. Logical implication of two statements can be proved either by truth table or by the rules of inference. Notation for logical implication is this. Now, let's invite one of my friends that are going to teach you about logical implication by truth table.
Hello everyone, today we are going to explore logical implication using truth table. In logic, we say one statement logically implies another if the second statement is always true whenever the first one is true. Let's look at two examples, one purely mathematical and one translated from everyday language. In our first example, we want to determine if not P and Q implies not R, then that logically implies not Q or R. To do this, we construct a truth table with 8 rows to cover every possibility for P, Q, and R. We calculate the truth values for our first statement, which we will call A, and our second statement B. For a logical implication to be valid, the conditional statement A implies B must be a tautology, meaning it has to be true in every single row. As we can see from our result, the final column is not all 1 because it is not a tautology. We conclude that the first statement does not logically imply the second. Now, let's apply this to a real-world argument. The problem states, if you like apple, you will like the pie. If you like this pie, then you will like the bakery. Therefore, if you do not like the bakery, you do not like apples. To solve this, we first define our primitive statement. P is you like apple. Q is you like this pie. R is you like the bakery. Next, we rewrite the argument in symbolic form. We join our premise using the AND symbol and indicate the conclusion with an arrow. This gives us the formula. The final step is to construct another truth table for this new formula. If the final column is entirely true, then the argument is valid. This process shows us how truth table act as a powerful tool to verify the consistency and validity of our reasoning, whether in math or daily conversation.
Does my friend explanation clear to you? I hope so. Now, earlier today, you have learned about logical implication by truth table. Now, let's take a look on what my friends They're going to teach you about logical implication by rules of inference.
Implication is the process of proving that a specific conclusion follows naturally from a set of premises, while truth tables are one way to check for validity. They can be inefficient. Therefore, we use rules of inference as a standardized way to analyze logical implication. First, we have modus ponens, rule of detachment. This rule states that if we have a conditional, if P then Q, and we know P is true, we can conclude that Q. Next, law of syllogism. This allows us to chain logic together. If P implies Q and Q implies R, then P logically implies R. Next, we have modus tollens. If P then Q, but Q is false, then P must also false. Next, we have rule of conjunction. If we know that P is true and Q is true separately, we can conclude that P and Q are true together. Rule of deduction syllogism. If we have a choice of P or Q and we know P is false, then Q must be a true. Next, rule of conjunction simplification. If we know that P and Q is true, we can simplify this to say that P is true or Q is true individually. Next, rule of deduction implication. If P is true, we can logically state that P or Q is true because only one part need to be true for the whole statement to work. Next, I have rule of contradiction. If we can show that not P lead to a contradiction or a false statement, then P must be true. Rule of conditional proof. If we assume P and Q are true and that P lead to Q implies R, then we can conclude R. Next, we have rule of proof by case. If P lead to R and Q lead to R, then P or Q will always lead to R. Next, constructive dilemma. If P implies Q and R implies S, then having P or R lead to the conclusion Q or S. Last, destructive dilemma. This is the opposite. If P implies Q and R implies S, but we know not Q or not S, then we can conclude not P or not R. Let's walk through our first example of proving a logical implication using specific rules. I will go to prove that the conclusion P is valid based on three starting premises. Step 1. We start with our first premise, which is if R then S. Step 2. Our second premise tells us that S is false, written as not S. Step 3. By combining these two using the modus tollens rule, we can conclude that R must also be false or not R. Step 4. Now we look at our third premise, which is if not P then R. Step 5. Since we just proved that R is false in step 3, we apply modus tollens again to step 4. This tells us that the initial condition not P must be false, leaving us with not P. Last step. Finally, we use the law of double negation to simplify not P to our final conclusion P. This proves that entire logical string is valid. For example 2, now let's look at the slightly more complex proof where we use the law of syllogism and conditional statement to reach a conclusion of Q or S. Step 1 and step 2, we begin with our first two premises, P implies R and R implies S. Step 3. By using the law of syllogism, we can write these two to conclude that P implies S. Step 4. We introduce our third premise, which is if not P then Q. Step 5 and step 6. We take the third premise and apply the contrapositive and double negation rule to flip it into if not Q then P. Step 7. Now we can create a new chain. Since not Q lead to P from step 6 and P lead to S from step 6, The law of syllogism tells us that not Q implies S. Last step, step 8 and step 9, to reach our final goal. We convert this conditional statement into the disjunction not Q implies S is logically the same as not Q or S, which simplifies via double negation to Q or S, the implication of proven valid.
Now, do you clear about the rules of inference my friend have teach earlier? Great! Sometimes the question on this subject, logic and elementary proving method, can sometimes get a little bit trickier. They will ask us to find the truth value of primitive statement using invalid logical implication. How we do that? Don't worry, we are going to take a look on one of my few friends that are going to teach you about how to find truth value on primitive statements using invalid logical implications.
Okay, now I will explain about invalid logical implication, that is, truth values of primitive statements. An implication statement is false only if the hypothesis is true and the conclusion is false. If there are many statements which relate to conjunction in the hypothesis, all the statements must hold true values for the hypothesis to be true. The statements in the hypothesis are called premises. Thus, the implication statement that has more than one premise and one conclusion is called argument. We will discuss on the validation of the logical argument by using rules of inference. Truth values for all primitive statements can be determined for invalid logical implication by using the concept of false implication statements.
Example of invalid logical implication, true values of primitive statements. Question: find the true values for P, Q, R, S, and T if the following statement is false. The question is, open bracket, the quantity Q implies to R and the quantity not P or T and not S, and the quantity not T and Q close bracket implies the quantity T and S. One way to solve this problem is by constructing a truth table. The application statement is false when T and S is false. Now, the conjunction statement is false. Therefore, both T and S should be false. Meanwhile, the premise Q implies to R, not P or T, not S, not T, and Q all must hold true values since the hypothesis is true. The details are in the following table. So, the following table is T is 0, that is false, S is 0, that means false too. So, the not of the S and T, that is 1 and 1, that means true. So, the not T and Q, that is 1 because of Q is 1, so that means it's true. Q implies to R, that is 1, that means it's true. R is 1, that is true. Not P or T, that is 1, that is true. Not P, that is 1, and P only is 0. And lastly, T and S, that is 0. Therefore, the true value for each primitive statement are as follows. P is 0, that is false. Q is 1, that is true. R is 1, that is true. S is 0, that is false. And lastly, T is 0, that is false. The following is another technique via truth table using the different approach. The given application is false, so it is understood that the hypothesis is true and the conclusion is false. That means 1 implies to 0.
Now, we have almost reached the end of our video. Now tell me, do you enjoy our teaching? That's great to hear. Now, what do we learn about today's lesson? What is the conclusion of our lessons today? Logical implication is a structured relationship between a set of premise, the hypothesis, and a conclusion. Whenever an argument is valid or invalid depends on the truth value of its individual of components. During our lessons during logical implication by truth table, we have learned that a logical implication A implies B is only considered valid if it a tautology. This means that in every possible scenario, every row of a truth table, even if there is one instance that hypothesis is true but the conclusion is false, the implication is invalid. Now, from our learning about finding logical implication by rules of inference, the rules of inference, like modus ponens or modus tollens, are pre-proven templates for valid argument. If an argument follows one of these 12 patterns, you don't even need to build a truth table. The conclusion is guaranteed to be logically follow from the premise. Now, based on our learning about finding truth table is on primitive statement using invalid logical implications, we find that to prove the implication is false, you must find specific set of truth value where the hypothesis is true, but the conclusion must be false. This is a shortcut method used to find given value without drawing a massive truth table. Thank you for joining our learning session today. I hope you learned something from us watching this video and might get some implication on how to solve a question about logical implications. Thank you so much. Bye.